Recently proven that a Riemann-Stieltjes integral is going to be defined provided that the integrand function f is continuous and the path function gamma is bounded variation. Now, we have a good accounting for continuity. We have many ways to prove that a function is continuous, but we don't yet have a very detailed understanding of bounded variation. So we need stronger conditions on gamma that will guarantee that it is a bounded variation curve. Now, you might expect that differentiability would be the right condition. Continuity is clearly not enough. Perhaps if gamma is differentiable, then it has bounded variation. But this lecture is an illustrated counterexample to that idea. Here, we're going to look at the path gamma, which is defined by the formula t squared cosine pi over t squared. And we're going to have a close look at this function, and we'll see that it is differentiable everywhere, in fact, but it is not bounded it doesn't have bounded variation. Now, as for differentiability, differentiability away from zero is easy. We can just use the differentiation formulas to actually calculate the derivative of that. That's no problem. Differentiation at zero is a little bit of a chore. Let's look at a graph and I'll indicate how we prove differentiation at zero. So we've got some imports here and some code to produce a graph. Here's a graph of the function gamma. What you'll notice here is that the oscillatory behavior of the cosine is basically inverted. Instead of having infinitely many crests and troughs here in the cosine function evenly spaced throughout the x-axis, we have infinitely many of these oscillations packed and approaching zero. That's because we have pi divided by t squared inside the cosine. But because we have this t squared out here, this function is actually squeezed between two functions, two different parabolas indicated here. This parabola y equals x squared, and this parabola y equals minus x squared. And because it is, when we calculate the derivative at zero, then we can use the squeeze theorem to say that the derivative at zero, that the limit involved is trapped between the limits of this orange function and this green function. And so it's not very hard to show that the derivative of this function at zero is defined and equal to zero. This function is not continuously differentiable, though. Notice that the derivative, that these oscillations get steeper and steeper, and so you would expect the first derivative of this function would get larger and larger, large positive and large negative and large positive and large negative, and then suddenly zero. So the derivative is not continuous, but it is defined at all inputs. Now, our job here, our goal is to show that this function is not bounded variation. And so bounded variation is about partitions, and it's about what happens when we take the variation of this function gamma with respect to a partition. So I'm going to hide these functions and reveal another piece of information, which is a sequence of values here. What I've done here is I've calculated some x values, which are the tops and bottoms. Actually, they're not. If you look closely here, this is not exactly the maximum. These are the x values at which the function gamma meets the parabolas. So actually, the red values here are not the exact maximum value, but are the meeting points with these parabolas. But no matter, we've calculated some special x values. And these x values have the form 1 over the square root of n. So I think this one is 1 over the square root of 2, 1 over the square root of 3, 1 over the square root of 4, etc. So these are 1 over the square root of n, and they capture the locations where this function gamma meets those parabolas. Now, what's important about these? Well, it's because of the way we've rigged the function here, it's actually fairly easy to calculate the values of this function at the special points 1 over the square root of n, and we'll do that shortly. What we're going to do is we're going to imagine that we have a partition here which has breakpoints here. These are going to be the TIs in a partition. Now, a partition cannot have infinitely many breakpoints, and so I can't continue this sequence forever. Let's just imagine that we have a few of these points and then we stop. I think here I've gone out to the point 20. So I've got a sequence of values up to 20. But because of the way this function works, it'll take the 19th as the last. So this must be the 19th point here. So we're going to take a finite list of these values, and then we're going to calculate the x values associated to them, which are 1 over square root of n, and then we're going to calculate the y values associated to them, and then we're going to use them to calculate the variation of gamma with respect to a partition that contains these endpoints. So let's do that, and we'll see that we can prove that gamma actually does not have bounded variation. So what we need to do is we need to look at these values, xn equals 1 over the square root of n, and we need to calculate gamma at these values. So all we do is we take the formula. So these values are not equal to 0, so we can use the first formula. We just plug in these values for the formula of gamma, and we get 1 over root n squared cosine pi over 1 over root n squared. So the squares and the square roots cancel by design, and this gives us 1 over n cosine pi n. Notice the n moves to the top, and we get pi n here. So that's simple, but cosine pi n is even simpler than that. If n is even, then cosine pi n will be 1. If n is odd, cosine pi n will be negative 1. And so we can rewrite cosine pi n as minus 1 to the n. And we just get an alternating harmonic here. So this is just an alternating harmonic. These are the values gamma applied to the points xn. So what we're learning here is that gamma here is exactly 1/2. Gamma here is minus 1/3. This is positive 1/4, minus 1/5, positive 1/6. So the gamma values at these points are the alternating harmonic. Now, what that means, because they alternate, when we calculate gamma of xn plus 1 minus gamma of xn, when we calculate this difference, the signs differ. And so one of these will be positive and one of these will be negative, and they will combine there. So it doesn't matter which one is positive and which one is negative. The modulus of, or absolute value in this case, of this difference is always going to be the sum of 1 over n and 1 over n plus 1. So for example, if we're taking positive 1/2 minus negative 1/3, then we'll get 1/2 plus 1/3. If we're taking minus 1/3 minus positive 1/4, then we'll get 1/3 plus 1/4. So we always get these things positively here. So if we sum these up to a certain point, which would be 20 in this case, or 19 in this case, if we sum all of these up, then we get a sum of terms like this as n goes from 1 to some value, some limiting value cap n. And such a sum will always be greater than an initial segment of the harmonic series. Now we know that the harmonic series diverges. And so if this sum is always going to, it can be made greater than an initial sum, of the harmonic series, then that means that it can be made arbitrarily large. And so these sums like this can be made arbitrarily large. Now we can't let n go to infinity because we're still reasoning about the variation with respect to a partition. A partition can only have finitely many points, but a partition can have arbitrarily many points. And so we could add 1,000,000 of these or 1,000,000,000 of these, and we would still have a partition. So for certain partitions, the variation with respect to that partition can be made as large as you want. That means that the variation of gamma with respect to a partition can be made arbitrarily large by designing the partition correctly, and that means the gamma does not have bounded variation, at least not on any interval that contains 0.